talk a little bit about HPCS and I/O. Cray had a very interesting announcement today on the web. I won't put him on the spot, but you may have to find out what that's all about later. So www.cray.com if you want to see that announcement. But John's been working on this project for 3 years, and it's coming to fruition. We're working with Cray on this, and it's quite exciting, some of the direction that it's taking. So with that, I'll turn it over to John.
Did the speaker come across okay, or I guess this is I'm John Carrier, and I'm the I/O lead for the HPCS program at Cray. So what I want to do is, in the agenda, is first off talk about what DARPA is about and what the HPCS program is, and then how Cray is involved in HPCS. Then the next is to talk about HPCS I/O and what our plans are, what the goals that Cray has for HPCS I/O, and then how Luster plays a part in that, and what Sun is doing with us for HPCS. First off, DARPA is it's a branch of government, or a government agency. It's the Advanced Research Projects Agency, and it's a part of the Department of Defense. And they have a program called HPCS, which is High Productivity Computing System. It's not high performance productivity. And so what they did is they started a competition amongst several vendors to come up with designs that would allow the mission partners for DARPA to have high performance computing, high productivity computing in the 2010-2011 time frame. The focus of the system is DARPA is a lead agency, and there's mission partners that are consulting with them. So you'll hear me mention mission partners several times. So there's actually HPCS, that's one group, and then the mission partners are actually a separate group that we also talk to with the device on the system. In 2006, DARPA awarded 2 HPCS program grants, one to IBM and one to Cray. These are sizable budgets. They're going to fund research into these new systems through 2010, 2011. And the goal is to make the systems more productive. So it's not just trying to get very large systems. The idea is to have something that when the users are ready to get port their codes to them, that they have a much shorter time from the time to sit down at the console and actually reading results. So from Cray's approach to this is, what are we doing for this? Part of it is dealing with parallel codes. And amongst the parallel codes that we're looking to get access to are shared memory codes, so that we have a global address space. So things like Co-Array Fortran, global arrays, VPC, as well as our new program language we call Chapel, are meant to extend the ability of users to have their code be reflected on the systems. And Chapel in particular is designed so that the details of the underlying computer are somewhat abstracted, so that the user writes to an abstract expression and that the compiler then actually determines the parallelism that's there. And parallelism is important for these programs because Cray has several different technologies we use. One of them is the vector processors that are good for data level parallelism, and the other are multi-threaded processors that are used for multi-threaded parallelism. And what happens in our systems is that the compiler determines what's the best mode for these codes to run and automatically switches based on how the code is written. The focus for Cray is we have this thing called adaptive configurable computing, and what we're really trying to do is make it so that the system adapts to what the code does, rather than having to have the engineer or the programmer adapt their code to the system. So it's trying to make the system more productive, or make the engineers more productive when using our computer. Our roadmap is, what we're looking to do is, we have currently a scalar line, a vector line, and a multi-threaded line. Our scalar line is started with the Red Storm project, XT3. We've now expanded that to XT4 and XT5, soon to be XT6, which is the Baker program that Shane mentioned before. We have the vector lines, now X2 going on to XT5H, and then a multi-threaded line, the XMT. these will all converge in the final HPCS program. We've identified two subgroups for these programs. One of them is Baker, and Baker is focusing mostly on the scalar line and bringing out the new network infrastructure that's going to be used to link up the different processes in our system. And then the final program is Cascade, which is introducing the new processors that have a combination of vector, we call it multi-threaded vector processing. So it's being able to combine both types of specialized processors that will happen. I'm sorry? It's actually on the same silicon. The question was, is the combining the multi-threaded and the vectors in the same motherboard or the same silicon? It's actually the same silicon. It's the same chip. It can be programmed in one mode, it's a vector processor, and another mode is an array of multi-threaded processors. And the compiler takes the runtime, the compiler takes advantage of switching between those based on directives that it gives from the user, or else it's able to figure out itself. Our system architecture for Baker and Cascade programs are based on our XT system, and we have a massively parallel processing system. It's a proprietary interconnect that is linking up multiple nodes. And the point of this slide is that there's two partitions. There's the compute partition, which are nodes that are sitting out on this high-speed network, and then separate from those are I/O. The compute nodes are only doing processing. We've only got one task, and that's the user's application. The I/O nodes are where most of the guts get done of talking to external file systems, or for dealing with logging sessions and job logging and such. So for Lustre, for HPCS I/O and Lustre, everything is focused on the service partition. So that's the platform we're starting with, and then where does this go with HPCS I/O? So the next set of slides, they're busy. Their tables are full of data, and I don't really want to go through it all. I'm happy to, but I don't. I'm putting in the slides so that it's on record. A lot of there's been an evolution of the HPCS program and what we're looking at for craze up to HPCS goals. We have, as Kevin said, I've been working on this for 3 years. We started off with original requirements from DARPA, and then we received feedback along the way from mission partners as well as the HPCS program. And so what we consider to be our goals are the result of those inputs from DARPA itself as well as from mission partners. And so I've got these slides. The intent was to have this stuff public. I could ask a number of vendors for it. This is a way of getting it out. So if you've got questions, I'm happy to answer. But a lot of this stuff has come up today in different contexts. But if they're busy and it seems like I'm flying through them, feel free to slow me down. My intent is on the first part about HPCS I/O is that DARPA gave us 5 requirements. So the initial solicitation was 5 issues: streaming I/O 32 bytes a second, 32,000 file crates per second, and 30,000 nodes. They wanted 1 trillion files in a single file system, and they wanted 10,000 megabit operations per second. So if you look at those just together, it doesn't really make any sense. To make sense out of it, though, it's really there's 2 different environments that the mission partners are targeting. There's one group of users that are focused on what we call capture I/O. Capture I/O is where there's a large shared memory, and there's a data source that data is streaming into that large shared memory, where an application is running to find the beginning and start of find the beginning of the file and then the end of the file, and then push all that data off to the file system. So it's focused on a single, really it's looking at client performance, how to get the most performance out of a single client platform. The parallel environment is much more of what we think that Lustre is exceeding in, where you have thousands of clients talking to a group of shared file servers. And so the requirements for the parallel environment, that's where they want the really large file systems, really looking at how to stress the servers, not the clients. That's where I is much more about sharing or stressing the client environment. To help us, after they gave these scenarios, after they gave us these requirements, partway through close to the end of the actual phase 2 proposal writing time, Henry Newman over here gave us a list of 12 scenarios. And you look at these scenarios and it's a bit overwhelming, but what provide some context, is that there's really two groups of scenarios. There is a group of capture environments they want us to test against, and a group of parallel environments they want us to test. So this is in a document that is available out on the web. The idea is that they give a set of test scenarios, what they're looking for, and how we should set the test up, and then give a result. And instead of looking at absolute performance for any one of these tests, instead what they want is to have us show a scalability. So if we're able to go and take a set of storage and get a number on it, if we increase the number of disks or we increase the number of file servers, then we should see a scalable change, some sort of linear change in performance. And a lot of them, some of them they're looking for between 80 to 85% of whatever the theoretical bandwidth of the storage is. What Henry was hoping that we would show in going through these scenarios is that we need to find, look at the storage system as if it was Amdahl's, you're doing the Amdahl's law, just like we think of parallel processing and apply Amdahl's law to parallel processing. We should look at our I/O system in the same way and look for the bottlenecks and try to see the limits of scale. So, and then again, last summer, we got some more input from the mission partners. Again, there was a survey, a set of questions that we had all asked, IBM and Cray had asked, and the answers that came back were to help clarify where the requirements were. So now we've gone from 5 requirements to some even more. So they gave us more information about the capacity. It's not just 1 trillion files in the file system. They gave us 10 billion files in the directory. They gave us a range in sizes of the files. Performance, well, they said they wanted 32,000 file crates before. Now they really want 40,000 file crates in a second. And reliability is the big thing that's been added to the list. Is that there's a recognition that to get through 1 trillion files, you have to have so many disks, and there's such a chance for undetected bit errors as these disks, these spindles are getting larger and larger, that there has to be something else besides simple RAID or RAID 6 to help detect these errors. So the overriding message is that they wanted something called T10 diff or its equivalent. T10 diff is a spec within the T10 or ANSI T10, and it adds a number of bytes to the actual data blocks. And they get generated, it can be generated all the way up to the application layer and then move down through the I/O stack and eventually be laid out on disk with blocks. So that there's a mechanism at any point along that chain to how the data is being organized, how the data is being returned in storage, or retrieved. Actually, storing is one way, so retrieving it. So that's a big thing. The other thing on here is the file system uptime, the bandwidth availability, is that with numbers like this, 99.99%, there really is no time for the file system to be down. The disk system has to be up. So they're looking, the mission partners are asking the HPCS vendors to step up and come up with a solution that lets them do real-time research. Instead of having to take the file system down, the system needs to be set up. The other thing they did is gave us suggestions for data access. So in here, there's just some things. One of the things we looked at is like the POSIX I/O extensions that are being considered in the open group. So right now, there's some concerns about POSIX is great if you're dealing with a disk that's right on it's a locally attached disk. But if you're dealing with a network system and you're sharing that resource amongst thousands of clients, it does cause latency, it does cause problems in performance. So the open group is considering this, a bunch of HPCS extensions that are being considered. There's also issues with metadata being used. Some of the mission partners use the metadata actually as a data record. The files are 0 length. The metadata itself is the record. So those are suggestions that they came up with. Now, from the mission partner suggestions, from the HPCS requirements, the scenarios that we received to help us evaluate our system, Craig came up with a list of goals that we have for our I/O. We broke it up into 6 categories. And this is what we're working with this with Sun to target features that we can add to Luster to help us achieve these goals. So metadata performance, we're looking at, looking at 40,000 file creates from a single client or 10,000 metadata operations from multiple clients and through the files, through the directory tree. We're looking at I/O performance of 30 gigabytes per second from a single client, but we're also looking at 240 gigabyte a second list of value that we're trying to keep supported with the open project. Capacity, again, is a trillion files, there's no change there. And 30,000 clients, we now know is a low number. We're expecting our number of clients to be getting up to the 100,000s. IOPS targets are 10. Actually, that hasn't come up. It's specific IOPS, it's metadata IOPS, but not actually block IOPS. Have any other comment on that? So the answer is that hasn't come up. It's metadata is more important. It's been the most important feature that they mentioned. And even the actual bandwidth numbers that the IO mission partner suggested were nothing compared to what numbers that the Open is trying to get for the system. Okay. Let's.
8 gigabyte.
Okay. There is something we can. If you have a question about this, you can email me. I'll send it to you. The other ones we're looking at scalability, reliability, and client accessibility. So the scalability is just that we're acknowledging that we're going to have to do these HPCS IO scenarios, and that whatever file system and storage solution we come up with, we're going to have to apply the scenarios that DARPA gave us to that system. And again, the importance there is demonstrating scalability. It's not the absolute performance of the system, it's just showing that as you increase the number of resources that are used, you get a linear increase in performance. It's why it's scalable. Reliability is another feature, and I mentioned that because that is important to Luster solutions that they propose. And then client accessibility are things we're looking at, but there's nothing that a lot of these are future technologies we're just going to track. Now, where does Luster play? This is the Luster user group. So where's Luster and Sun play into this HPCS IO spectrum? Well, Cray has had a long relationship with Sun. We started out with cluster file systems on our XP3, and we deployed that. We were one of the first. Sandia became one of the largest deployments early on for Luster, and we've maintained that relationship in all of our subsequent platforms. So when we saw this HPCS proposal from DARPA, it was logical to go to Sun and say, or cluster file systems, and ask them what they could do for us. Peter Brown saw it and thought it was a very exciting challenge, and immediately signed up to help us out. So we've extended that relationship, and fortunately, with the transition to Sun, the Luster work that we've been doing, we've got a good, strong relationship with our existing programs, and they're continuing to support us for HPCS IO goals. So the initial proposal from Peter Brown, when we saw the original requirements, we saw two main challenges. The first was the size of the file system. The fact that you're trying to get a trillion files in a single file system. That meant that you had to have the back-end storage had to be hardened, because if that many spindle behind it, if they were trying to spend time rebuilding the file system or correcting themselves from errors, that they would never get the performance on targets they were trying to. So they were trying to harden the file system. The next thing was trying to deal with cluster metadata and also increasing the size of the file system. When they started this, ZFS wasn't a possibility, so they were looking at what they could add to OpenSFS, what could be DHC3, and then changing all the data structures and actually making DHC3 look more like ZFS. And the other big challenge is the capture node on the single. When you're looking at a single node, how do you get file creation rates and database to match that? And that's what we've heard today about the metadata like that cache. The other issue we're adding here is central file IO application. We've got a bunch of small IOs. It's not just the metadata operations that you get cache, but being able to aggregate multiple IO, small IO RPCs with a single RPC. So we broke these in the features we're looking at. I broke them into from those challenges into server side and client side. So the server side, file system hardening, this is where I think ZFS comes to play. I don't know that's official line from Sign, but in the evolution of their discussions, early on they talked about making EXP3 more like ZFS, and just to go to ZFS makes a lot more sense to kind of retrofit EXP3. They're also looking at changes to file system performance because you've got as Peter said today about the storage, the open storage platform, more of this being done in software that can actually take advantage of software ready. And if they're doing that, they want to add very new clustering and distributed sparing in order to make the rebuild times from the but to allow the system, the disk to be able to rebuild more efficiently to live. And then also the cluster metadata servers lets you to scale into the files, and it also gives you a chance to do another. The client features, the big one for today is the right metadata, right back cache. It's something that started, and it's came out of this program that we're looking at it, but it's obviously got other uses that they're introducing right in progress. The file IO aggregation, again, in this case, files are starting. Right now, there's end-to-end checksums that occur between the client and the server. With ZFS, there's going to be checksums going to disk. They're looking to come up with a single end-to-end checksum, something that can be issued on the disk and somehow developed into the disk. So starting on the client and moving into the disk. But that's just one of the a future to consider. So that's where Luster is with HPCS and IO. And the conclusions from this is that so DARPA is funding Crane's system, hyperconnectivity system. It's part of the HPCS program. There are a number of challenges that we're looking to solve, and Luster is an important factor for Crane. It's our selection for the file system, and the Sun is working with us to meet these challenges, and the parallel IO and the other challenges. And as we've heard today, with many of these features that come because of HPCS IO that are given to these customers. That's it. Questions? So I heard one already about the number of IOPS. Was there, Henry, did you put that?
Yeah, it was, 5 gigabytes of files, requested 512 bytes, 2 gigabytes of IOPS with the same distribution.
So from 512 bytes to
64K.
64K.
With a random distribution.
Okay, then random distribution aside is from 512 to 64K. There will be 5 gigabytes of read and 2 gigabytes of write. As I said, there's a lot of data in those slides. It glazed over worse than far, but we're looking at all that. So thank you for letting me share that. Oh, yeah. Mm-hmm. No. That's something that will be added as part of the HPCS program. So the question was on file IO aggregation, if that was a feature now. It's not. It's part of the HPCS program. Yes, sir. When does Crane move to ZFS? We have not started testing with it yet. When it's available, we will start testing. But we're just as interested as everybody else to see if the performance is going to be up. Any other questions?